make sure I'm recording. So I did move the lab to Friday. So if you're still working on that lab and need some time, I moved it over so you guys can spend a little bit more time on it. I'll probably do that with the ones in the future too. Just I'll leave the labs where they are for right now, so because you guys can work on them whenever you want. But if it gets to be a little bit like, okay, this one takes some more time, I'm happy to move them. You guys, I want you guys doing those and make sure you get them done, but I don't want to put a lot of
So I
time
submitted
pressure on you.
mine.
If you did use a late pass for it, I can see that and I can give that back. Um,
Okay, I submitted mine, but I think I might have messed up on the second portion of it. Are we able to
I can
go
have my
back
headphones
and
on or I can't hear
resub?
anything.
Oh. Sorry. What I was saying was I submitted mine yesterday,
Mm-hmm.
but now kind of like looking back at some of the material, I think I might have messed up on the second portion of the lab. Are we able to go back and resubmit it? Or
Absolutely.
okay, all right, thank you.
And feel free to do that. That's great. It shows me, what does it show me? It shows me the last one submitted. I can go in and look at the others, but if you could submit, like I had somebody submit 4 of them yesterday because they were having just some trouble with the submission process. So yeah, no problem at all. Now let's see. Oh, also I looked over the discussion board. I assigned some points for the discussion boards. Do make sure you keep in mind those discussion boards, one, are part of your homework scores, and what? Okay, and you are responsible each week for making sure you make one new post, and that you reply to some post. So I will be looking for both of those things. So a lot of you this week only had a post, um, which means you only got half the points for it. I am going to modify that so because it's the first week and we're still figuring all this out, so that won't cost points against anybody for this week if they only did one and not both. But for the future weeks, make sure that you're doing both of those. Let's see. If you have any other questions on the lab stuff or homework stuff, let me know. I have gotten a handful of nice questions about that lab. So keep those coming if you have questions. Okay, anything that you guys want to look at or talk about before we jump into today's information? Okay. Yesterday, we talked about measures of center. So we talked about, again, averages. And specifically, we talked about the 3 main types of average that we're going to work with: mean, median, and we won't work too much with mode, but every once in a while mode will come up. And the big distinction of them was that mean was our average by value. Our median was average by position, so the values didn't matter as much, just the order the values were in mattered. And mode was our average by frequency, essentially. It became our most common data point we had as our mode. Of these 3, you may remember us talking about the median as a resistant measure of center. So that meant that it was resistant to the effects of weird numbers, of extreme large or extreme small numbers. Didn't throw the median off very much, where it did throw our mean off. Oftentimes you'll see these data graphs. So you'll see a graph of some particular data, and it will have, you know, a nice curve on it. This axis, as it will generally be for us, will be frequency, and this axis is some sort of amount, either a measured amount of length or weight or gravity or whatever it happens to be. This is usually some amount, and this is almost always for us a frequency. Anytime you're looking at one of these, you can often express your mean, median, mode. We kind of have a sense of where those things should be based on what this graph looks like. That highest point, for example, that highest point is the point where it has the most frequency. So that highest point is going to be always our mode. About halfway through this data, usually really close to the peak, but halfway through the data, so that half the data is on one side of that blue line and half the data is on the other side of that blue line. It's not necessarily the highest frequency, though it's often very close to it, but that point such that half the data is on this side, half the data is on this side, you can think of it as the area under the curve on that side has the same area as the area over here. That's our median, the center by where all these are positioned. And because this has values that pull way out this way, there's a bunch of data in here, a bunch of amounts in here. If this was, say, the weight in pounds of, I don't know, a steak, why not? Then you got, you know, a couple steaks are these little tiny steaks. Most of the steaks are around this size, so they're, you know, 8 ounces, 10 ounces, 12 ounces. But you've got, you know, those some huge porterhouse. Okay, now I'm going to make myself hungry. Some real big, huge, giant steaks out here. Those big steaks are going to take our mean average and pull that mean out towards these large values. So that mean is going to be skewed from what wants to be the center. It's going to skew it out towards that small, thin tail. Since it's pulling out towards that small, thin tail, and that thin tail is to the right, we refer to this as being skewed right, or having right skew. If, on the other hand, let me change the color. That's okay. If, on the other hand, our graph had a lot of small values, had a lot of small values, and then a big bump of values at the end. So there were some values that were really tiny, but most of the data was fairly large out here. We would still have our median relatively close to the top of that peak. Our mode is always the top. But these small values would again take our mean and pull our mean down, this time towards the left, skewing our mean towards the left. Our mean, which I should just call X bar, that's the symbol we're going to use for it. And that would skew that mean towards the left. So oftentimes people get the skew backwards, and reasonably so. This graph looks like, well, most of the data is on the left, so why isn't it skewed left? We're not looking at where the data is skewed towards. When we talk about skew, we're following that mean. Were there extreme values that skewed the mean from the center? So if the mean went to the right, then it's skewed right. If the mean is being pulled off to the left because of these extreme values, then it's left skewed. We talked a little bit about that yesterday, but you'll see it a lot in terms of graphs in your textbook and in your homework and so forth. So I did want to look at it a little bit in terms of graphs. Lastly, one of the other possibilities, there's lots of possibilities, is that our graph is fairly symmetrical. It's got, that bump of data in the middle. We usually refer to this as a bell-shaped curve, but it's fairly symmetric, where the amount on this side is about the same as the amount on that side. When that happens, the median and the mean are often very close together. They're not always the same. If it's perfectly symmetric data, they'll be the same, but things are rarely perfect. But when the mean and the median are close together, that generally tells us that our data is fairly symmetrically distributed. So you might get questions like, how do you know this data is symmetric? Oh, the mean and the median are close together. How do you know, or is this skewed left, skewed right, or symmetric? Well, my mean is a lot higher than my median, so my mean has been skewed to the right, or my mean is a lot lower than my median, so my mean has been skewed left. Questions about that? We happy with that? Cool. I mentioned before, it is handy to have your guys' cameras on. If you're okay with that or comfortable with that, or if you can kind of push yourself to be comfortable with that, it does give me a surprising amount of information, just kind of being able to see where you guys are, nodding, yeah, or going, what was that, or whatnot. And it also helps all of us feel a little more together in this, so it can help us in setting up the making good discussions in the forums and all those kinds of things. I can certainly understand if you don't want to for any reason. You might be in FBI witness protection and not want your face anywhere, or, well, that's about the only real good reason. It's also, who wants to have to, get themselves cleaned up enough to be presentable? You don't have to be presentable. I won't judge you. I'm going to pick on you guys every day about that from now on. Okay, we'll work on that. So what we want to talk about today is something that often goes along with our measures of center, something that actually always should, but unfortunately too often is left out when we talk about centers. And that is, we want to talk about the spread. An A in spread, right? That looks like spread. Is that how you spell spread? Okay. We want to talk about the spread of our data. And to give you an example of why this can be important, one of the things that is common when you have a baby, particularly your first baby, everybody wants to know what they should expect when they have a kid. And so you're always talking to either pediatricians or other parents, or looking at advice somewhere, and ask things like, okay, how long should it take for my child to start walking or talking or sitting up or turning their heads? And one of the things that always irritated me is you'll ask something like, oh, how about when they should start walking? And they'll tell you that, a kid will start walking at about, or on average, 11 months. That always irritated me a lot. For one thing, they never told me what type of average, whether it's a mean or a median. But even if we assume it's a mean or assume that the data is fairly symmetric and it doesn't matter, this information that the average, I'm going to specify that the mean average for when they walk is 11 months. That's still very little information. It's not enough information for it to be really useful. For example, if your kid is 11 months and 2 days old and not walking yet, should you panic? Now, some parents do. It's been 11 months and a couple days. My little Johnny's not walking yet. Oh no, what's wrong with Johnny? Or if they are walking, say, a week early, it's only been 10 and a half months. Does that mean your kid is a walking prodigy? No, probably not. But again, people will often go, my Timmy walked at 10 months, so he's clearly going to be an Olympian. The problem with this is we're not given any idea of how much spread this should have to it. Okay, an average of 11 months, but is 11 months and a couple of days the kind of spread we're talking about? Is it 11 months and a couple of weeks? Is it 11 months plus or minus 3 or 4 months? What should we expect in that range? When should I start to worry, or when should I be really proud, is an important part of that. So when I was particularly pediatricians, whenever they would say something like that, I would ask them, what's the spread, or what's the standard deviation? We'll talk about that today. And oftentimes they'd look at me and say, I remember that word from school. I was always, I want some useful data here. So knowing whether it's 11 months plus or minus 3 days or 11 months plus or minus 4 months, that can be an important part of understanding how data is distributed. So I want to spend some time today and talk about our different kinds of spread. We'll actually spend a couple days on the spread. They can be a little bit calculation heavy, and they're not, a lot of people understand what average is, but the ideas of our spreads take a little bit more talking through. So we'll spend a couple of days on each of them. But one of the things to keep in mind is, just like we have different ways of finding average, we are going to have some different ways of talking about spread. We have a way of finding average based on value. So we will have a way of finding spread based on value. We have a way of finding center based on position, which is nice and resistant. So we will have a way of finding spread, which is based on position, which is resistant. Mode we won't talk about much in terms of spread, because categorical data, we don't care as much about for now. So the type of spread I want to talk about today is called standard deviation. And hopefully that can sound a little bit like spread. Standard deviation, how much we deviate from the center, how much our data is spread, how much it changes on the standard. Standardly, how much is our data deviating? Standardly, how much is our data spread out? And I really want you to tightly associate the idea of standard deviation, as we talk about it, with mean. Mean and standard deviation really go together. Mean is a way to find center based on value. Standard deviation, correspondingly, is a measure of spread based on value. Just like mean was fairly calculation heavy, we had to do all the adding up, we had to do the dividing. Standard deviation is a little bit calculation heavy because all those values matter. When we do median, median will have its own sense of spread. It's called interquartile range, IQR. We'll talk about that more in a day or two. That's going to be less calculation heavy. It's going to be more about having the data in order and looking at where things are. So it will be resistant and based on position, just like median is. So be starting to try to associate these things together. These essentially form a pair. If somebody tells you the mean, you ask for standard deviation. Somebody tells you a median, you ask for interquartile range. And again, we'll talk about what that means later. So I want to shift over here and have a nice little chat about standard deviation. For that, it might be handy for us to have some data. So let's have some values here. Let's say 4, 5, 6, 6, 7, 7, 7, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9 data points. 9 should be fine. Now let's get one more, 11. So we have 3, 3, 3, yeah, 10 data points here. So our n is equal to 10. And if we want to find standard deviation, again, our standard deviation is how much does our data deviate from some sort of standard, some sort of center. Standard deviation. So essentially what we're going to be finding is how much on average does this data deviate from the center? What is our standard amount of deviation? You can think of it as what is the average amount of deviation from the center. Well, if we want to know how far we're deviating from the center, it would be nice to know what that center is. So our step one for finding standard deviation is to find our center. Our center for standard deviation is our mean. Remember, we associate mean with standard deviation. So the center we're deviating from is going to be that mean. So I'm going to give you a minute or two. Find that mean for this set of data. When you have a suggested mean, throw it over in the chat. We'll see if we all line up there. Alan, Ivan, both 6.8. I got 6.8. I trust us. Anybody have any questions on where that came from? You guys are all very quiet today. I know, Alan, right? Andrea wandered off. I think she's doing some work, but Ivan's been playing along a little bit. maybe later we'll do some quizzes or something, and that usually gets people involved. So anyway, so our standard deviation. So our 6.8, that's our center. So that's what we're deviating from. So for each of these values, we need to find the individual, I'm just going to abbreviate the individual deviations. So that's essentially how far do each of these data points deviate from our mean. So for each of them, for each of our values, the 4, the 5, each 6, all the 7s, the 8, and the 11, for each of those values, we want to find how much do each of them deviate? How much do each of them slide away from this center? So again, take a moment. Ideally, you've got paper, pencil, and you're taking notes and following along with this. Do that. If not, doing it for yourself later is going to be harder. So if you need to rush off and grab some paper and pencil, do it. I won't be able to see you anyway, for most of you. So for each of these, we want to find this difference. Do make sure the subtraction happens in this order, the value minus the mean. So our 4 minus 6.8 is going to give us something negative. So find all those individual deviations. Go off to my notes over here. Give you a chance to finish that up and catch up. Alan, negative 8.8? Yeah, I'm not sure what you're typing there. Okay. Yeah. Oh, gotcha. So one of the things I want you to do, well, first off, I'd like to make sure everybody's okay with where all this is coming from. So other than Alan, who's let me know what's going on. Miranda, Ivan, Tessa, Alex, Andrea, are where are these values coming from making sense? Give me a thumbs up or a yes or a no, Andrea.
No, sorry, I had to step out, so I didn't see how you got those.
Oh, yeah, no problem. We're finding the individual deviations of all of this data. So we found the center, the mean of the data, and then we're asking, okay, how far are each of our values from that mean? So we're taking the values specifically in the order value minus mean. So the 4, in terms of our language, the 4 deviates from the mean by negative 2.8. Tells us how far, the 2.8, and in which direction, negative, because it's less than that mean. So all of these form our individual uh, deviations. Now, I want you to take a moment and add all of those individual deviations together. If we wanted to find something like the average of these deviations, we'd want to know things like what are their sums and so forth. So add up all those deviations and see what you get. This is something we're going to need to do on that homework, so make sure you're trying to follow along. I know it's a lot of calculations. This is one of the few things that we do that has a fair amount of chunky calculations. It does not look like a confident 0. That's a more confident 0. Anybody else get 0? Good. It should be 0. And hopefully, when we think about it a little bit, Alan got -2. There's something in there then that like probably this 4.2, be careful with it. It should add up to 0. And that's actually a nice fact. You can test to make sure your deviations are correct by adding them up. Because anytime we find our individual deviations, their sum should always be 0. If these are decimal approximations, sometimes you get a decimal approximation for 0, so it can sometimes be a little bit off because of those approximations. But fundamentally, they should all add up to 0. And the reason for that is exactly because this mean is our center. So if our mean is there, then where our other data points are, some of them could be further out, some of them could be closer, but the sum of everything on this side and everything on that side of the mean should balance out. Some of them might be further away, some of them might be closer, but if this, if you imagine this being like, say, a big board with weights on it, and we put a little teeter-totter right there, if it's the mean, it should balance on that point. All the weight on one side should balance with all the weight on the other. So everything on the negative plus everything on the positive should add up to be 0. That's one of the reasons the mean is often called the center of mass, because in physics, that's how we find center of mass. So these deviations will always do this, add up to 0. And that makes finding the average a little bit difficult, because if we're trying to find the average of our deviations to get a standard deviation, then adding them all up and dividing by how many we have isn't going to help, because they will always add up to 0. So we've got to do something about that before we try to find an average. also, we're trying to examine the amount of spread here. So it might be good for us to try to emphasize spread. And we can emphasize spread by making these small amounts of spread matter less, and these big amounts of spread matter more. So there's a nice way to accomplish both of those things, to stop these from adding up to zero while emphasizing the variation we have. And that's to take each of these individual deviations that we already found. So this is the x minus x bar that we found here. That's these values. Take those values and square them. Squaring them will automatically make them positive, so they'll stop adding up to zero, and it will make the big deviations larger and the smaller deviations even smaller, emphasizing the big deviations, minimizing the small ones, and really emphasize our amount of spread. So you probably need a calculator for this one, but go through on your tables and square each of these and see what values you get when you square each of those. So make another section of your table here for the squared deviations. So square deviations. Give you a minute to do that. You guys need to be prepared because I'm going to need your help. I'm going to have to ask you guys what all these squares are. So I'm going to need you guys to have answers for that and be able to kind of check each other. So be prepared to help me out with that. Ideally, if you've got a calculator with you, they should go fairly quickly. You can imagine that if we had, say, 100 data points, doing this all by hand would be a pain. And it is a pain to do it with lots of data points. We will get to a point that we can get the calculators to do this fairly automatically, or Excel, gosh, Excel can do this with a couple of clicks once we learn how to do it. So don't worry too much about all this by hand. We want to see it happen by hand a couple times, and you've got a couple homework problems that'll walk you through it. But once we get comfortable with the idea, we'll eventually kind of stop doing it by hand each time because it does take a while. But we want to really make sure we understand what we're doing here first. So can you guys tell me what negative 2.8 squared is? Probably 8 something. 7. That's 7 seems reasonable. Almost 8. 42 is a little too big. This is almost 3, and 3 squared is 9, so it should be a little bit less than 9. So that's 7.84 sounds more reasonable. 7.84. So the negative 2.8 quantity, make sure you have the quantity so that negative squares. 7.84 sounds reasonable. What about the negative 1.8? 3.24, it seems reasonable. Again, this is almost 2. 2 squared is 4, so a little less than 4. Makes sense. What about negative 0.8? Good, Ivan. And actually, we know 8 squared is 64, so that 0.64 shouldn't seem too surprising. Do notice these got bigger when we squared them. The bigger one got bigger. The smaller one got bigger, but not by as much. And these 0.8s actually are getting smaller. So it is doing what it's supposed to do in making our large changes larger, emphasizing them, and making our small changes de-emphasized. These 0.2 squared, what is 0.2 squared? Good, 0.04. So there's 2 decimal places there, so 1, 2 decimal places. The 2 squared is 4, or just ask the calculator, but you have to be a little bit careful. Nice thing. We know we have that a bunch of times. What about this 1.2 squared? $1.44. Good, that seems reasonable. And again, 12 squared is 144, so that looks reasonable. 4.2 squared. It should be somewhere around 20. 17.67, that's believable. 17.64. And again, notice our big deviation got super expanded, got super emphasized. So just in case here, just for clarification, let me grab that. Where'd it go? Oh, there's. Grab that calculator. So we're just taking those values like the 1.2, squaring it. We can square it by either raising to the second power or by taking something like the 1.2 and using this x squared button. We'll square whatever we have there. We do have to be careful with the negatives. Because we want those negatives to be squared, we got to make sure we use that negative. So negative, I think 2.8 was one of them. I can't see my other board now. End that parenthesis, square that. Should give us things like that 7.84. So if the calculator use gives you any trouble, let me know. We can set aside some time to look at those. That's where those are coming from. Okay, that's probably the big long step in this, is all those squares. But just like before, we're going to be trying to find sort of an average of these. It is only going to be sort of an average. So we do want to do what we normally do for averages. It didn't work here because these always added to 0, but because these are all positive and nicely emphasized, we're not going to get that 0 anymore. We're going to get something we can work with. So again, we do want to find the sum of all those squared deviations. So do take a moment and add those all together. Okay, again, this is probably the long step, all that adding. So take a moment and find that sum. So we've got a private suggestion of 31.56. And do keep in mind that you can send me little private messages if you want to be that, shy, which is fine, but still want to kind of suggest stuff. Andrea, 31.56. And that seems reasonable. We got, 17 and 7. That's going to get us into the 20s, but most of the rest of these are really small. So, getting barely into the 30s, that seems quite reasonable. So that's going to be our sum. I've got the same thing. Cool. Yeah, I feel pretty confident about that. That 31.56 seems pretty good. So that's going to be our sum, and it's going to act like the sum that we found when we found an average. But there's a couple things we have to do. We've got to take this. I do feel compelled to have each one of these steps be a different color, and I don't know why, but I'm going to go with it. So we do need to take that result, the x minus x bar squared. We summed them all together. Remember that sigma symbol we used for sums the other day. So we summed together all of that stuff. So that's our 31.56. And if we were finding a normal average, we would divide by n. We divide by how many values we have. But standard deviation is a little bit weird. Excuse me. When we're doing it for a sample, because instead of finding a strict average here, we find what's called an adjusted average. Instead of dividing by our entire sample size, n, we're going to be dividing by n minus 1. So instead of dividing by 10, we're going to divide by 9. Now, why that is, the answer to why that is a little bit complicated. It has to do with a couple of different things. One, it has to do with the degrees of freedom within the problem. Don't worry too much about why, but if you want a little bit of an explanation, there's actually only 9 degrees of freedom in this problem, because if we knew 9 of these numbers and we knew this average that we're using to find this, having 9 of them and the average, we could compute the other one. So there's not 10 things changing in this problem. There's really only 9 things changing in this problem. I know that's weird because there really is 10 data points though, but it really does end up making a difference. We'll use degrees of freedom at the end for something else. Don't worry about why we have to do that so much. It is a fairly complicated discussion on exactly why it's necessary. But also, because we're doing a sample, samples tend to be more varied than populations. So, or at least have the opportunity to be more varied than populations. So dividing by less than the full n, dividing by 9 instead of 10, makes our standard deviation a little bit larger and accounts for the fact that it's a sample instead of the population. So there are a couple reasons we do it. And again, they can get fairly complex as to exactly technically why. But it's just, for us, it's just going to be, that's how we find it. But it is still essentially an average. It's just an adjusted average. So let's find that. Find the 31.56, the sum of our squared deviations. Divide that by 9, see what we get. $3.50. 3 seems reasonable. 3 times 9 would be 27. 4 times 9 would be 36. So something in between those. 3.5. Looks like it's, Ivan, you said it's 506. So if we round that to 2 decimal places, I would go 5.1. I'm actually going to grab a couple of these. 50667. Now, why am I rounding it to 5 decimal places? No particular reason. But this isn't our final answer. So I do want to carry a couple decimals so we can make a final answer that's a little bit more accurate. If this was our final answer, I would have stopped at the 3.5 probably, or at least the 3.51. But there is something else we have to do, so carrying a little bit of extra decimals will help us stay accurate. But that number does seem reasonable. It's a little bit less than 4, so that seems like a reasonable answer for that division. Now, I said this isn't the answer, and it's not, but it's close. There is actually a name for this number. It's called the variance of the data. And variance should sound kind of like spread, and it is kind of like spread. So often this number is used to discuss spread, but it has a slight problem to it for our uses. And that is, whatever these x values are, let's say all of these x values are some number of feet. Like, how many feet of fence did we build today? Well, one of the days, a bunch of the days you built 7 feet of fencing, a couple of days you built 6 feet. You had one really good day, you built 11 feet of fencing. So that means this average of 6.8 feet would be an average number of feet of fencing you built each day. Okay, great. So again, this 4, 5, 6, 7, 8, 9, all of these are feet of fencing. That means these deviations are feet, how much each day deviated from our standard in feet of fencing. So these are all still feet. But as soon as we square it, these turned into square feet. So this sum is a total square feet. Dividing that square feet by 9, the units on this variance is square feet. I don't want my spread to be in square feet. I want to know how much my spread is in feet, because my data is in feet. So we squared this on purpose. We squared this for a reason. We squared it so we could, make these positive and enhance some of our variation, and it served that purpose. But before we're done, we have to essentially fix the fact that we did that by taking this whole thing's square root. That square root will turn our feet squared back into feet. So we'll have a nice meaningful value. And this square accomplished its goal. So now we can essentially get it out of the way by square rooting the whole thing. So we need to square root this value and see what we get. Then we'll be done. And see what you get when you square root that. I'll get you started. It should be 1 point something. .8726, 1.87, 1.8726, so on, so on, so on. By convention, we generally round descriptive statistics to one more decimal than the original problem. So the original problem was in whole numbers. So I am going to, by default, round this to one more decimal than that, so tenths. Your homework will often ask you to round to 2 decimal places or even 3 decimal places. Follow those instructions. But I'm just going to do this by default because it is a fairly standard default for statistics. Because we took that square root of our feet squared, this deviation or standard deviation is now back to being in feet. So 1.9 feet is our standard deviation. And we will, for sample, we will use S for standard deviation. So, other than to acknowledge that that's a lot of work, and it absolutely is, does this idea seem conceptually reasonable? We wanted to know how much our data spreads. So we found out how much each of the data points spread out from the center. We squared those to emphasize it and make it positive. found an adjusted average of that to find a type of average, and then took the square root to get back to our data. Why we have to square it, why we take this adjusted average instead, there are some details in that, but hopefully this idea of, we use some of those tools to find an idea of spread, hopefully that seems reasonable. Questions about that so far?
I do have one quick question. How did you get the 31.56 divided by 9? Where'd that 9 come from?
That 9 is, again, our adjusted average, our sample size minus 1. Since our sample size is 10, we had 10 data points. That 10 minus 1 is the 9.
Okay, thank you.
Sure. It's a little tough since we wrote that n equals 10 down, like, I don't know, 20 minutes ago. So it's easy to lose track of it. So that's a good question. Anybody else? Ivan, Miranda, is that all good? Also going to encourage you guys, if you don't like to type for whatever reason, or don't like to have the camera up so you can nod at me, you can use the thumbs up button. If you go next to the to thing in the chat, you should have your chats open as well. If you don't know how to find those, let me know. But if you go to that little more button with the 3 dots in your chat, there should be a thumbs up button there. Or if you go to your main Zoom menu and under manage participants, there's a whole bunch of choices there. You can click yes, no, go slower, go faster. There's all kinds of little nonverbal communications you can give. It is really helpful if you guys can be giving that feedback. Not only will you get more out of it, but we'll all get more out of it, and I won't have to keep stopping and staring at you guys, or staring at your names anyway. So I would like to see the kind of input from you guys uptick a bit. Miranda Gomez, you found the thumbs up. Great. I love the thumbs up. That's a nice way to say, hey, we're good. Ivan, awesome. Yeah, that thumbs up is a great way to do that. Okay. So again, calculating this standard deviation, it is a fair amount of work. No one would argue that. The nice thing, as I said before, is we will learn how to make either the calculator do this for us. The calculator is a little bit of a pain because typing all this data into the calculator can be a little bit of a pain. But Excel is great at doing this. Once we get ourselves more comfortable with Excel, we'll have, a big list of data like you did on your lab. You can literally highlight that data, hit a couple of buttons, and it will throw this number out at you. Actually, it'll throw all the decimals of accuracy you want at you. So we will get to a point that we won't be doing this by hand. Do you need to practice doing this by hand a bit? Yes. The homework assignments will ask you to do it at least a couple of times by hand for those of you who started playing with those homework assignments, which is great, playing a bit ahead. You've seen it kind of walk you through some of these. And that's good. We want that practice because we want to make sure we understand where this is coming from so we can put it in perspective. But a really important part, and probably the most important part of this, isn't how we calculate it, but what does it mean? What is that telling us about our data? Particularly if this is just a sample of data and we're trying to apply this to a overall population, what does this 1.9 feet tell us about our population? How is it telling us spread? So let's look, let's imagine. We did talk about this in terms of feet. So I'm going to stick with the feet of fencing as a metaphor, but these numbers could, of course, stand for anything. Our average amount of fencing, our center of our data, was that 6.8. So we could certainly say, on average, how many feet of fencing? It's okay.
Yeah.
No problem. We can imagine on average, somebody asked us on average, how many feet of fencing do you build a day or whatever this is? 6.8 feet of fencing, that's an average day. But again, that doesn't tell us much about, well, how high can that be or how low can that be? It doesn't give us a sense of spread. This 1.9 feet, the standard deviation, is supposed to do that. What it says is if we go out that 1.9 feet in both directions from our center, that's going to give us a typical range that we can expect our data to fall in. And careful, I do use that word typical in a fairly formal way. Data is considered typical when it is within one standard deviation of your mean. That's what it means for data to be typical. So if we take this 6.8 and add 1.9, we'll get, what, 8.7? If we take the 6.8 and subtract 1.9, we get, what, 4.9? Yeah, that looks right. If that's wrong, let me know. So that average of 4.9 feet turns into a typical range of 4.9 feet to 8.7 feet. So having that combination of this mean and that standard deviation essentially gives us a typical plus or minus. 6.8 plus or minus 1.9 on a typical day tells us not only where negative, oh, this is, make sure it's the x bar minus s. So it's going to be positive as opposed to negative. But it gives us not only a center, but a sense of how spread out it's going to be. So if somebody says, hey, can you do, 9 feet in a day? Yeah, they can do 9 feet in a day, but that's not a typical day. So this range within one standard deviation we call typical. Now we can go out further than that. Let's say we go out 2 standard deviations. So add another 1.9, so that would be what, 9, 10.6, 10.6, and back another 1.9 is going to be, oh, nice even 3. That's handy. And again, those are feet. Feet. So that gives us a second interval. This second interval is 2 standard deviations from our mean. 2 standard deviations from the mean, it's bigger than our typical range. We usually refer to this as our usual range. So data is usual data if it's within 2 standard deviations. More specifically, we often talk about what it means for data to be unusual. If your data is unusual, it's outside 2 standard deviations. So you are usually within 2 standard deviations. You're typically within 1. So again, could they do 10 feet in a day? Well, it's not typical to do as much as 10 feet, but it's not unusual either. Before I let you go, we can do one more. Actually, you can do as many as you want. You go out 3 standard deviations. That would be, what, 12.5? And out another one down this way. That would be, what, 1.1? So that range at 3 standard deviations from the mean should contain almost all your data. How much is almost all? Well, we'll talk about that next time. We do have a fairly technical amount for almost all, but this 1.9 number gives us a really nice way to look at, okay, 6.8 is our average, but what are our expectations? Well, typically we expect it to be between 4.9 and 8.7. It's unusual for it to be more than, or sorry, less than 3 or more than 10.6. So, usually it's in this range. Typically it's in this range. Almost every fence building day falls between 1.1 and 12.5. And you can see all of our data fits in that range. So most of these values, the 5, the 6, the 7s, and the 8, all of those data points would be considered typical because they fall in that typical range. This 11 is unusual. It's outside 2 standard deviations, so we'd say this 11 is unusual. This 4 isn't unusual. It's not less than the 3, so it's not outside 2, but it is outside typical. So this 4 wasn't a typical day, but it's not unusual either. All of these were typical. That 11 was as far as unusual. So I gotta let you go today. We do have, we're gonna go through all this again at 11:40 if you guys wanna watch through it again. I also am recording this, so I'll put this up if you guys wanna watch through it again. We'll talk more about standard deviation tomorrow, do a little less calculation heavy version of it. But does this idea of finding a number to be able to talk about how our data is spread, does that idea make sense? Good, I'm good. So play with this tool. Again, it is calculation heavy. Don't let that make you too nervous. For the most part, we will just be needing to interpret it. We will practice doing it, mechanically a bit, but really the super important part for us is getting this idea of what it's telling us, about where our data is. And we'll talk more about that tomorrow. If you guys have any questions or anything comes up that you need, let me know. And other than that, have a wonderful day.
All right, thank you.
Thank you guys. Have a good day.
Bye.
Darby, you're here for the 11:40, as I recall. So I'll clean up my station here. And then I'm going to go grab something, so I'll be back in a couple minutes and we'll start that.